log odds of disease. And on top of that, we're assuming, again, additivity. We're assuming that the effect of being a male rather than a female is measured by B1, regardless of your level of smoking. The gap between these two straight lines is the B1 term. It says non-smokers, 1-pack-a-day smokers, 2-pack-a-day smokers, 3-pack-a-day smokers. Males have a higher log odds than females because the gap between these two parallel lines is the same. The gap is equal to that number B1. Likewise, it assumes the effect of smoking is measured by this B2, and that doesn't depend on whether you're a male or a female. The model assumes that the two straight lines have the same slope, but the effect of smoking is the same regardless whether you're a male or a female. So those are the two assumptions, additivity and linearity, that are being made in this model. The previous model was assuming a step function model, and the archaeces sort of suggests that maybe this linear relationship is reasonable to assume because the value for the AIC for this model was lower than the value for the AIC for the step model. Okay, now let's talk about this assumption of additivity for a second. This model assumes that the effect of smoking, measured by B2, is the same females. B1 term is the same regardless whether you're a non-smoker, a 1-pack-a-day smoker, or a 2-pack-a-day smoker. But what if that weren't true? Let's talk a little bit about that. Well, if that were not true, we would have something called effect modification. If the previous model were not appropriate in terms of its additivity assumption, that means we would be assuming that the effect of males versus females was different for different levels of smoking. Maybe non-smoking men versus non-smoking women are no different in terms of their risk. But maybe heavy smoking men are much different from heavy smoking women. So maybe the effect of male versus female is modified, changes by your level of smoking. And the previous model assumed that was not the case. The previous model assumed that the effect of males versus females was a common value, B1, regardless of the level of smoking. So even though it was controlling for potential confounding by smoking, it was making an added assumption that smoking was not an effect modifier, that the effect of males versus females was the same fixed value, regardless whether you're talking about males and females who are non-smokers, or males or females who are 1-pack-a-day smokers, or males or females who are 3-pack-a-day smokers. Well, if that were not the case, how would we change our model so that our model would reflect that the effect of smoking could have different effects at different levels? The effect of male could have different effects at different levels of smoking. Well, to do that, we have to introduce something called an interaction term. What an interaction term in statistics is just the product of two of our risk factors. We have a risk factor in the previous model called male. 1 if you're a man, 0 if you're a woman. A variable called PAX, which is 0, 1, 2, or 3 by the amount of smoking you have. Now let's make a new variable called male PAX. I can call it anything I want. I'm going to call it male PAX. It's a new risk factor, which mathematically is nothing more than the product of a person's value for male times his or her value for PAX. So if you were a 1-pack-a-day male, your value for male PAX would be 1 times 1 of 1. If you're a 3-pack-a-day smoking male, your value for male PAX would be 1 times 3 of 3. If you're a female who doesn't smoke, your value for male PAX would be 0 times 0, or 0. So your value for male PAX depends on your value for male and depends on your value for PAX. And now let's consider a model that does not make an assumption of additivity. Let's consider a model that is slightly different from what we had before. Now we're going to say your log odds of disease is equal to B0 plus B1 times male plus B2 times PAX plus B3, a new term, B3 times male PAX. What does this model assume in terms of the relationship that smoking and gender have on your risk of developing heart disease? Here's the model again. And let's think about if you are female, your value for male will equal to 0. So the B1 times male becomes 0. Think of that term being disappearing. And likewise, your value for male PAX for a female is always going to be 0 times her level of smoking. It's always going to be 0. So for a female, this model becomes B0 plus B2 times PAX. And that's, again, it's a straight line. So this is the straight line linear relationship that the model assumes for females. The intercept of this line would be B0. The slope of this line would be B2. you're a male, your value for male is 1. Your value for male Pax is 1 times whatever Pax is, so it's going to just be the same as Pax. So for a male, this model becomes a B0 plus a B1. Added to it, a B2 times Pax plus a B3 times Pax. Because male Pax is the same as Pax for a male. So that means you have a new line, an intercept now which is B0 plus B1, which is different from the intercept that females had as long as B1 is non-zero. And a new slope, which is now B2 plus B3, which is different from the slope the females had, namely just the B2, as long as the B3 is 0. So now what we're assuming, again, is that cigarettes or Pax has a linear relationship in terms of the relationship to the log odds of disease, but the slopes are different. So now the model says, if you look at what's the effect of being a male versus a female, well, for a non-smoker, it'll be the gap between these two lines when Pax is equal to 0. What if you are a 3-pack-a-day smoker? Again, it's going to be the gap between these two lines when Pax is equal to 3. And notice the gap between the lines is different when Pax is equal to 3 than when Pax is equal to 0. This model allows the effect of males versus females to be different, to depend, to change, or to be modified by the level of smoking. Likewise, this model allows the effect of smoking to be different from females from males, because we have different slopes in these two lines. So if you want to allow for the existence of effect modification in a regression model, the way we do that is to include an interaction term like this. Allow the model, in this case, to have two different slopes for the lines for females and for males, and as a result, we have different gaps, different distances between those lines when we compare males to females at different levels of smoking. But what happens if we fit this model for the data set? Let's go to the model itself. Here's the coefficient for estimate for B0, for B1, for B2, and for B3. The first thing we do is we look at the coefficient for B3. Because notice, if I go back to the model, 2 slides ago, if B3 were equal to 0, what I would have is the same model I had before, B0 plus B1 plus B2. So how can I decide whether this model that allows for effect modification, that allows for the males and females to have different slopes when we look at the relationship between cigarette smoking and your log odds of disease, how can I decide whether this model is better than the previous model? I can do it a couple of different ways. The easiest way to do it is look at the coefficient for estimate for B3 and ask, how significant is that coefficient? If I divide B3 by its standard error, I get a number 2.19. That corresponds to a p-value of 0.14. That means there's no significant difference between this model that had the B3 times male Pax added to it and the previous model that just had male and Pax in it. Male Pax is not a significant predictor in this model. And therefore, you might say, I don't need that interaction term. I can drop it and go back to the previous model. And essentially what I'm doing is testing for the existence of effect modification. So if the interaction term were significant, you can make a strong argument for needing to include that factor in the model. If the interaction term is not significant in this case, that means we cannot reject the null hypothesis that B3 is equal to 0. If B3 is equal to 0, what we have is this term here essentially drops out of the model because B3 would equal to 0 if the null hypothesis is true. And I'm left with the model I had previously that did not have the interaction term. So in many ways, what we're hoping for is that the interaction term would be non-significant, to justify not having to include these interaction terms. Because if you do include these interaction terms, your interpretation of the other coefficients becomes more difficult. That's the slide I just skipped over. Remember, here's our model, B0 plus B1 times male plus B2 times Pax plus B3 times male Pax. What does this model talk about the effect of being a male versus a female? If you're talking about non-smokers, Pax is equal to 0 for those people. Male Pax is going to equal to 0, regardless of whether you're a male or female. So a male non-smoker